In section 10.2, we're going to review solving systems of linear equations in several variables. We're really going to focus on 3 variables. The simplest type of system in 3 variables is this one here, which is called triangular form. So the way we go about solving this is we actually already know one of the solutions. One of the solutions is z equals 3. You're going to substitute it into the previous equation, and then we're going to be able to find out what y is. So y plus 6 equals 5, so y must be negative 1. And then you're going to take that answer and this answer and plug them both into the original equation. So x minus 2y is negative 1, minus z is 3. So x plus 2 minus 3 equals 1. X minus 1 equals 1, so x is equal to 2. The solution to a system of 2 variables was called an ordered pair. So if you have a system with 3 variables, we call the solution an ordered triplet. And it's still written like an ordered pair. It's just that there are going to be 3 numbers, and you put them in alphabetical order. Alphabetical order. So x, y, z. In this second example, this system in 3 variables, we're going to use a process called Gaussian elimination in order to solve it. In order to solve the system, we only know how to solve systems algebraically if they have 2 variables. So what I'm going to do is I'm going to create 2 new equations that only have 2 variables. In order to do that, I'm going to call this equation 1, this equation 2, and this equation 3, just because it helps me organize the information. First, I'm going to decide what 2 variables will go in my new system. And the way that I'm going to decide how I'm going to do it is I'm going to notice that if I add equation 1 and equation 2 together, it's already set up to eliminate the y's. So when I add them, I get 2x plus 2z equals 14. Now what I'm going to do is I'm going to add equations 2 and 3 together. So I just added 1 and 2. Now I'm going to add 2 and 3 together, and I'm going to eliminate the y's again so that I only have x and z. In order to do that, I want you to notice that both of them have a positive 2y, so I'm going to have to change the sign on one of them. So why don't I multiply the first equation, not equation 1, but let's multiply this equation by negative 1. So I get negative x minus 2y plus z equals negative 13. I'm not going to do anything to the second equation. And now my y's are opposites, and I can add this together, and I get 2x minus 4z equals negative 10. I take these 2 new equations, and I'm going to solve that system like I solve any other system, and I'm going to figure out what x and z are, and then once I know x and z, I can plug those back into one of these 3 original equations to find y. So my new system is 2x plus 2z equals 14, and 2x minus 4z equals negative 10. The easiest way to solve this system is to multiply one of the equations by negative 1. I'll multiply the second one. And then my x's will be opposites, so negative 2x plus 4z is equal to positive 10. 6z is equal to 24, so z is 4. So now I know one of my 3 coordinates. I'm going to plug that back into one of these 2 equations to find x. I'll plug it into the first one. So 2x plus 2 times 4 equals 14. 2x plus 8 equals 14. 2x equals 6. So x equals 3. Now I know x and z. I'm going to plug it back into one of the 3 original equations to find y. And it doesn't matter which one I pick. For no apparent reason, I'll just pick the first equation, which was x minus 2y plus 3z equals 1. So x is 3 and z is 4. 3 minus 2y plus 12 equals 1. Negative 2y plus 15 is equal to 1. So negative 2y is equal to negative 14, and y equals 7. So my ordered triplet is 3, 7, 4. Now, that was a lot of work, and some of these systems can be very complicated. So there's another way we have of solving this problem. As long as the equation is written in ax plus by plus dz equals c format. In other words, x, y, and z are all on the left and the constants on the right. You can put this in a matrix using the coefficients, just like we did with systems in 2 equations. It's just that my matrix is going to be a little bit bigger. Just a reminder, when doing matrices, watch out for negatives. One of the most common mistakes students make when using the calculator to solve this system is that they accidentally make something positive instead of negative, and it will throw off the entire answer. This particular matrix has 3 rows and 4 columns. So when you go put this into the calculator, you go to second x negative 1, arrow 2 to the right to edit. I'm running out of space. Hit enter. If the matrix does not say 3 by 4, just change it by hitting 3 enter, 4 enter, and enter each of your numbers into the matrix, remembering to hit enter when you're done to lock in the number. When you've typed in all your numbers, you quit. In other words, you go back to the home screen, and then you go back into matrix a second time, but this time you only go 1 to the right to math. Scroll until you find option B, RREF, which is reduced row echelon form, and hit enter so RREF comes up on the home screen. Then you have to go back into matrix a third time, and as long as you put your matrix into matrix A, just hit enter twice, and you should see pop up on the screen uh, 3, 7, 4. This part of the matrix is called the identity matrix. The identity matrix always has this nice little pattern of the ones on the diagonal. And as long as you see this nice pretty pattern, the last column is your solution in the order x, y, z. But as we know from systems in 2 variables, not all equations end up giving us solutions. So let's look at this system. I'm going to use a matrix now because I want to show you with a matrix how you're going to know if the answer is going to be no solution or infinitely many solutions. If you do the problem algebraically, it's no solution if you end up with something like, 0 equals 2 or 0 equals some number that's not 0 when you do your Gaussian elimination. In other words, if I add these together, get rid of one of the variables, add these together, get rid of one of the variables, and then I take those 2 new equations and try to solve for my 2 variables, the 2 variables end up canceling, and you end up with a false statement. And anytime all the variables cancel and you're left with a false statement, it's no solution. But it really is so much simpler to just plug this into the matrix program and have reduced row echelon form solve it for me. So when you plug this into your calculator and you go through the steps we just did, this is what you're going to see on the screen as the solution. This is not that pretty 100010001, is it? If the last row says 0001, this is the same as 0 equals 1, which is false. And in other words, it's going to be no solution. So you're going to know if your system has no solution if you don't get the identity matrix, and the last row says 0, 0, 0, 1. Well, how are we going to know if it's infinitely many solutions? Well, if you want to do this using Gaussian elimination, if you add these together and then add these together, you get your two new equations, and then you go to solve those two new equations in two variables, you're going to end up getting 0 equals 0 because both variables will cancel. Because 0 equals 0, we call that a true statement, and whenever the statement is true, it is infinitely many solutions. But how are you going to know using a matrix that that's what happened? So we're going to plug into our matrix 1, negative 1, 5, negative 2, 2, 1, 4, 2, 2, 4, negative 2, 8, and this is what you're going to see when you reduce row echelon form it. Again, you don't get the identity matrix. What I want you to notice is that the last row is 0, 0, 0, 0. That's 0 equals 0. And since that's true, it's infinitely many solutions. In example 5, Jason receives an inheritance of $50,000. His financial advisor suggests that he invest this in 3 mutual funds, a money market fund, a blue chip stock fund, and a high-tech stock fund. The advisor estimates that the money market fund will return 5% over the next year, the blue chip fund 9%, and the high-tech fund 26%. Jason wants a total first-year return of $4,000. To avoid excessive risk, he decides to invest 3 times as much in the money market fund as in the high-tech fund. How much should he invest in each fund? So let's define our variables. In the last section, we defined all of our variables as x and y. So in this section, we'll call all of our variables x, y, and z. So x can be the amount invested in the money market, because that was the first one listed. Amount invested in money market. Y can be the amount invested in the blue chip stock. And remember, you always want to identify what your variables represent. Z will be the amount invested in the high-tech stock. So we know that the total amount he has to invest is $50,000. So x plus y plus z is going to equal 50,000. That's going to be one of our equations. The second equation has to do with what percent of each fund he's going to get in a return. So the money market account is 5%, so that's 0.05. The blue chip stock fund was 9%, so that's 0.09. Oops, that's a y. And then the high-tech fund was 16%, and he wants his total return to be $4,000. The last equation has to do with the fact that he decides he's going to invest 3 times as much money in the market money fund as in the high-tech fund. That means that the money market is going to be 3 times the high-tech fund. So here are my 3 equations. I want to do a matrix. In order to do a matrix, all of my equations have to be in basically x, y, z constant format. So the third equation isn't. In order to put it in that format, it's really going to be x plus 0y minus 3z equals 0. Now I can create a matrix to solve this. So the first row of the matrix is going to be 1, 1, 1, 50,000. The second row is going to be 0.05, 0.09, 0.16, 4,000. And the last row is going to be 1, 0, negative 3, 0. So when you plug this information in the calculator and you use your reduced row echelon form, you're going to get this. Here's my identity matrix, so I must have an answer. And it looks like I'm going to invest $30,000 in the money market fund, $10,000 in the blue chip, and $10,000 in the high-tech fund. And that is section 10.2 on systems of linear equations in several variables.